So picture a computer, right? That's just been handed this totally impossible task. I mean, something it completely fails to understand. What does it do? It doesn't get anxious. It doesn't stress eat an entire bag of chips.
Yeah, it definitely doesn't lie awake at 3 a.m. just staring at the ceiling.
Exactly. It just throws an error code, stops, and waits for better instructions.
But then, picture a college student staring at a blank document the night before a huge thesis is due.
Or a professional who just got their 50th job rejection email.
The reaction by a person is so different. They don't just stop and wait for a new prompt.
They might panic or feel overwhelmed.
Which brings us to today's topic: computational thinking as a framework for problem solving.
It sounds like we're going to be talking about dark server rooms and lines of green code.
But interestingly, the same mental framework software engineers use when writing code can be used to tackle ambiguous life challenges, like graduating college or landing a career-defining job.
These concepts can help us take the overwhelming chaos of reality and transform it into step-by-step solutions.
Instead of just reacting to stress, we can proactively engineer a solution.
Okay, let's start.
Let's look at 5 aspects of computational thinking: decomposition, pattern recognition, abstraction, algorithms, and evaluation. The first concept is decomposition. This can help us tackle the very relatable tendency to look at a massive project and immediately feel completely defeated.
Decomposition. Break it down for us.
That is exactly what decomposition is. In software engineering, decomposition is the act of taking a large, complex system with far too many variables and breaking it down. Instead of something overwhelming, you have smaller, self-contained, manageable components.
Like taking a massive, chaotic pile of mixed Lego bricks and sorting them into groups by color or type.
Great example. And you might hear developers call this by other terms like modularization. This idea becomes incredibly important later when you encounter things like object-oriented programming.
Which sounds like something we're definitely saving for another episode.
Right. For now, the important idea is that we're breaking one overwhelming problem into manageable pieces.
Okay, so how can decomposition help with a problem outside of coding? Like, a job hunt is a struggle. It's so stressful.
It's paralyzing, right? But what if the large, ambiguous problem of get a new job is broken down into small steps, each one straightforward and clear, so you can accomplish it with confidence?
You mean something like, Step 1, update my LinkedIn profile. Step 2, update my resume. Step 3, research the culture of 3 target companies.
The problem already feels a little more manageable when tasks are isolated like that, because each of those steps is something I already know how to do.
Yes, I can easily picture myself completing those steps. But I want to push back on this a little bit.
Okay, go for it.
On a practical level, this sounds an awful lot like just writing a to-do list. If I write down, buy snacks, go to the library, do laundry, am I doing computer science? What separates true computational decomposition from just being an organized person with a notepad?
A standard to-do list is just a sequence of disposable chores. Once you buy the snacks, the task is no longer relevant. It has no future utility.
Right. I cross it off and throw the paper with the list on it away.
Exactly. But decomposition isn't merely listing something, like a set of chores. You're analyzing the structure of a larger problem and breaking it into meaningful subproblems that can be understood and solved independently or systematically. Once you do that, you might also discover reusable components.
Ah, okay. So it's about a deeper understanding of the problem as a whole and the subproblems that comprise it.
Right. And in computational thinking, when developers decompose software into modules, they often design those blocks to be reusable and extensible as a framework or an engine. If you decompose your thesis process effectively, you haven't just finished one paper. You have built an intellectual workflow.
Like a reusable template.
Right. You have a research module and a citation module that you can reuse with future papers.
And in the job hunt, if you write a highly adaptable cover letter module, you don't start from a blank page for the next application.
You are building a system of components that serve you indefinitely, rather than just surviving a one-off chore.
That really reframes the entire effort. You aren't doing chores. You are investing in building architecture that can be reused.
Perfect way to summarize it.
And once you have all these isolated, reusable blocks laid out in front of you, and you step back and look at them, you start to realize they aren't all unique.
Which leads directly into pattern recognition.
Right, finding the similarities.
Once your problem is broken down into parts, your next step is to find commonalities, like characteristics or underlying structures or behaviors.
Software developers do this to save time, right? I mean, so they aren't typing the same code all day?
If software engineers treated every single coding problem as a brand new, unique challenge, it would slow down development and innovation.
It would take forever to make a simple app.
Developers rely on established approaches, libraries, frameworks, and patterns, rather than solving every recurring problem from scratch.
Working smarter, not harder.
Exactly.
I see this playing out perfectly in job interviews too, because behavioral interviews are terrifying. It feels like there are a million different variables, and I need a lot of unique, perfectly rehearsed stories, but I think I only feel that way because I haven't applied pattern recognition. If I analyze those behavioral questions, they are just different interfaces for the exact same underlying prompt.
Hold up. Can you give me an example of that?
Okay, a question like, tell me about a time a project failed. And a question like, tell me about a time you had to work with a difficult colleague. Sound different, but they share the same structural DNA.
Are they both stress tests?
Yes, they are both testing resilience and conflict resolution. When an interviewer asks a complicated, multi-part behavioral question, I don't need to panic and invent a new answer on the spot. I just need to recognize the pattern and use a pre-built example I've previously prepared.
Recognizing patterns is revealing something a bit uncomfortable. We carry a lot of irrelevant information around. Once we see the core pattern, we can see all the noise surrounding it.
Which means we have to start filtering, right?
Yes, and filtering brings us to abstraction, which is focusing purely on the essential aspects of a problem. It means actively and aggressively filtering out unnecessary details.
Basically, the art of ignoring things on purpose.
That's a great way to put it, and it requires immense discipline. By identifying what is critical and stripping away what is not, we create a simplified representation of a complex system, which in computational thinking is called a model.
And the goal of a model is to communicate complex ideas clearly. An analogy for abstraction that really clicked for me is a map. Think about it. A physical map of a city is a highly abstracted model of reality. It shows you the roads, the major landmarks, and the distances.
Right, but it intentionally leaves out the color of the bricks on the buildings.
And it leaves out the specific species of trees lining the avenue, and the number of pedestrians walking on the sidewalk. If a map tried to include absolutely everything, I mean every detail of reality, it would have to be a 1-to-1 scale of the Earth.
It would be an incredibly accurate representation, but completely useless for navigation because it would be the size of the actual city.
Oh, accuracy is not the same as utility. And if we look at the job hunt example, the ultimate abstraction is a resume or even an elevator pitch.
A resume is literally a map of your career.
And yet, so many people treat their resume like an exhaustive autobiography, listing every task they completed on their last job. I mean, those facts are true. They did really happen, but they are like the color of the brick buildings on the map, details that can distract from a purpose.
Wait, hold up for a second. Career advisors, hiring managers, professors, they always tell you to be specific, right? They say, give me the concrete metrics. If abstraction is about zooming out and filtering noise, how do we not sound incredibly vague and generic in an interview? How do we balance abstraction with the demand for specific details?
Great point. That is exactly where the concept of abstraction is often misunderstood. Abstraction is not about being vague, it is about intentionality. A good model still has highly specific details, just like a map has specific, highly detailed road names. But a specific detail should only be permitted in a model if it directly helps the user navigate to the intended conclusion.
Meaning, the detail must serve the argument.
Yes, if you are answering an interview question about a successful marketing campaign, giving the specific percentage of revenue growth is a vital landmark. That's a detail you want to include.
Right. That is clear proof you did the job well.
But listing the weather details on the day of the product launch is not. You have to ruthlessly edit, filtering out the true but less vital facts so the interviewer can clearly navigate to the conclusion that you are competent and right for the role you are applying for.
Okay, let's recap where we are. We decomposed our massive problem into manageable blocks, then used pattern recognition, so we aren't reinventing the wheel, and used abstraction to filter out noise to build a clean, precise model.
Yes, but a model just sits there, right? It's static. To actually accomplish the goal, like, get the job or pass a class, we have to put it into motion.
We have to take action. We need to execute.
We need to use algorithms.
Algorithms. That word carries so much cultural baggage right now. At its core, what actually is an algorithm?
The core idea is that an algorithm is a set of steps to solve a problem.
Steps, as in a recipe with steps to bake a cake?
Yes, but there is a massive caveat to that analogy, isn't there?
A huge caveat. A recipe has some precise instructions, but it also has phrases like stir the batter until smooth or bake until golden brown. Those types of instructions make sense to me because we can interpret that. We have intuition, visual cues, and experience. We understand ambiguity.
We know what golden brown looks like, right? But if you feed a computer a vague instruction like cook until golden brown, the system doesn't inherently know how to define golden or brown.
Right. It requires absolute precision.
In computer science, there is actually a well-known set of guidelines for what qualifies as an algorithm.
Walk us through them.
Okay, 5 characteristics. The first is finiteness, which means the algorithm must eventually terminate after a finite number of steps. It cannot run indefinitely.
Finiteness. So it has to end.
Exactly. And the next is definiteness, meaning that every single step must be clearly and unambiguously defined, with no room for interpretation.
No golden brown?
No golden brown.
Okay. Definiteness, meaning no ambiguity.
Right. The third is input, and this can be nothing, or the algorithm can accept one or more inputs to start the process.
Input. It can run with none, or it can accept something. Got it.
The fourth is output, meaning the algorithm must produce one or more defined outputs. And that means that for an algorithm to be valid, it has to yield results that have a specified relation to the input.
Input in, output out. That makes sense.
And finally, the last characteristic is effectiveness. And that means that every step must be simple enough that it can be carried out accurately in a finite amount of time.
Let me make sure I've got this. We need an ending, clear instructions, inputs, outputs, and steps we can actually perform.
Perfect. You hit all 5 characteristics: finiteness, definiteness, input, output, and effectiveness.
Okay, let's put standard everyday advice to the test against these criteria. Think about the classic job hunting mentality. I'm going to wake up and apply to jobs all day.
If we view that statement through the lens of computational thinking, it's got problems.
Right? It lacks definiteness. Like, what does apply to jobs actually mean? Are you sending cold emails?
Are you filling out random web forms? Which industry? It's totally ambiguous.
It also fails finiteness. All day is not a finite, defined boundary.
And failing to define finiteness, you never get the cognitive closure of finishing. Defining a stopping point can make an overwhelming task feel more manageable.
So, how do we take a vague, stressful goal, like prepare for tomorrow's job interview, and engineer it into an algorithm?
Let's start with input. We need specifics, like the calendar invite for the interview and the job description for the role. Those are pieces of data we can feed into our system.
And we need definiteness and effectiveness. Clear, unambiguous steps that a person can realistically perform.
Right. Maybe something like, Step 1, read the job description and highlight the top 3 required skills. Step 2, check your resume for details related to those skills. Step 3, building on the information in your resume, Identify one specific detailed experience example for each of those 3 skills. Step 4. Stand in front of a mirror, set a timer on your phone, and speak the answers out loud twice.
There is zero ambiguity there. You aren't just getting ready, you're executing a defined action.
But we still need to define the output.
How about, the output is a targeted, verbally rehearsed interview strategy?
Good, I like that. And finiteness?
Yes, we need to define the boundary. I'm going to say that this entire process will take exactly 90 minutes, no more. When the timer hits 90 minutes, I close my laptop, walk away, and the preparation is complete.
Nice. You give yourself permission to stop. You terminate the program.
It feels like we have transformed a terrifying, ambiguous cloud of anxiety into a logical process that I feel more confident about. But what if it doesn't work?
Then we've discovered something important. Coming up with a solution is only part of the process. We also need to step back and ask, how well is our solution working? What did we learn? And what could we improve? This is where evaluation comes in.
I see. We identify what worked, what didn't, and what we might do differently next time.
Exactly. And that's a key idea in computational thinking and coding. Failure gives us information that helps improve the next version. The important thing is to ask, what did we learn and what should we change?
What a journey. We started this by looking at what seemed like a highly technical framework, and it turns out to be incredibly relevant to life challenges.
Yes! Whether you are staring down a mountain of homework or navigating the stressful landscape of a job hunt, you can decompose the chaos into isolated modules, leverage pattern recognition so you never have to start from scratch, use abstraction to filter out the noise, and create a model so you can build a highly effective, strictly defined algorithm to generate the result you want. Then you evaluate your solution and refine if needed.
Computational thinking is not a straight line from problem to solution.
It's a cycle of trying, evaluating, learning, and refining. The goal isn't to get everything right on the first attempt. It's to use what we learn to make our solutions better.
Thanks to those who joined in for our exploration of computational thinking. We hope you take these tools, build models, and start running some new algorithms out in the world.
Until next time.